Hello and welcome to 8.1 Energy Sources, video 2 of 4. This is the slide that we left off last time. So moving forward, and we're going to go ahead and skip this slide and move on to the next piece. And so this video is going to be focusing primarily on how the nuclear reactor works. It's going to be mainly conceptual, and we're not going to be doing calculations in this video. All right. Well, we saw in the last video that we have two types of energy. We have primary energy that's directly consumed by the user, and then there's secondary energy. Okay, so this is converted from another form of energy. So one example of that would be electricity. Okay, hydrogen would be another example if it's used in various vehicles. Right. Now, what we learned in the electricity and magnetism unit is that when you have a moving charge, it produces a magnetic field. Okay? The other way also works. If you have a charge that is stationary and that charge is exposed to a changing magnetic field, there will be movement of the charge. Okay, so for example, here in this slide, we've got an ammeter, so this is measuring current, and we've got wires going around. Okay, so this is a circuit. Here is a magnet. Now, whether it's a bar magnet or an electromagnet, it has some kind of magnetic field. Okay, so you can see the field lines coming out of the north pole of the magnet. Right now, when the magnet is stationary, there is a certain magnetic field here. But if the magnet is held stationary, the magnetic field in the region of this loop is constant. Now, if you move the magnet, so right now it's being moved towards, you would have noticed that the current was going clockwise. And as it moved away, the current went counterclockwise. Okay, so two things that we noticed right away: depending on the direction that the magnet is moving, the current will flow in opposite directions based on the direction of the field. Not to mention, when the magnet wasn't moving, there was no current. Okay, so let's just look at that quickly one more time. Okay, so magnet's moving, there's a current. Okay, no movement, no current. Magnet moving, there's a current. And if you paid attention to the ammeter here, it was also pointing in different directions to imply that the current was going in different directions. Now, in general, the ammeter won't tell you the direction that the current is flowing. To have that, you need something called a galvanometer. All right. So when you have this changing magnetic field in the vicinity of charges, which, well, there are electrons in this wire, all of a sudden they feel this push. And this push is called the electromotive force, and that's the voltage that will drive the electric current. Okay, so in this picture, we've got a gentleman inside of a generator, and there are many, many electrical coils in that generator. Now, those coils spin, and when exposed to a magnetic field, the fact that they're moving through that magnetic field means that they're moving through different regions of that field with different line densities. And if that's the case, that means it's constantly being exposed to different strengths of magnetic fields. Okay, this is how we generate electricity. We will see this and investigate this in much, much more detail as we study the nuclear reaction and nuclear reactor process, as well as the power generation plants fired by coal and oil. Okay, so in the animation at the bottom of the screen, you see various X's. Okay, that's telling us the direction of a magnetic field. On the bottom, we have a wire with various dots. These are the electrons inside of the wire. And what we're going to do here is manipulate the magnetic field. So when the magnetic field changes, so if it's moving up or down, notice that the current in the wire moves left and right. Now, current, there's two types of current. What you learned in grade 11 is that we have AC, alternating current, and DC, direct current. When studying electrical circuits, we focused on direct current. That meant that the electricity flowed in one direction. Here, you can clearly see that because the field keeps changing, kind of like the magnet that was going forward and backward, the electricity is going to keep reversing direction. That's alternating current. But even this scenario, even this will produce current. This is still movement of electrons. Whether it's moving back and forth, it doesn't matter. So for example, if you have a light bulb that's 60 watts, if it's operating at a certain frequency, let's say it's operating at a frequency of 45 hertz, That means the electrons are moving back and forth 45 times a second. Okay, so even though at that instant when it's changing direction as it moves back and forth, technically the current is off and the light would turn off, you don't notice it because it's turning on and off too fast. Okay, so this is alternating current, and this is why the current at your home is AC. Well, this reason, and also because it's easier to transport. DC and AC current have their own benefits and their own advantages and disadvantages. Okay, fossil fuel power stations. So coal is an example of a fossil fuel. Okay, so when you burn coal, this is chemical energy. Okay, so look at the bottom of this picture. So imagine there was coal down here at the bottom underneath this vessel. Okay, so you've got coal burning down here, and you've got essentially a tank of water on top. Okay? When the coal burns, it heats up. Okay, that heats up the tank of water directly above it. When water heats up, it will eventually reach boiling point, hence why it's called a boiler. Okay, when water boils, it becomes steam. Okay, and you see this orange pipe? That steam is going to travel through this orange pipe and head towards this gray rectangle here. Okay, that gray rectangle is a turbine. Okay, and that turbine is going to start spinning. When this steam pushes down on it, it's going to cause a rotation of the turbine. Now, these little black lines that you see on the rectangle, that is electrical wires. So these are coils. This is effectively a solenoid. Okay, so when these wires start turning, and they're turning inside an external magnetic field, so however the external magnetic field is generated, you have these wires moving in an external field, that will generate electricity in the wires. The fact that these electrons are moving within a field that's changing strength will cause the electron to start moving. Okay, but after the steam passes beyond this turbine, okay, after it causes the rotation, it comes down here into this box. This is a condenser. It cools down the steam back into liquid water, which then is pushed back into the tank, and the cycle repeats itself once again. Okay, so there we go. That gray piece in the animation, that's the steam. It's heading toward the turbine, rotates the turbine. Now, this large blue, dark blue rectangle, this is cold water. Okay, so if you pass steam through a region where there's cold water going through these pipes, it's going to cool down. It's going to cool down the steam. It's going to turn it into liquid water. Okay, so those of you who have really high-end computers in your homes, you might see there are various types of ways your computers can be cooled. And when I say computer, I'm not talking about a laptop. I'm talking about if you have a complete server set up in your room. Okay, so some people will cool down their computers using fans, but a lot of people will opt for a little bit more of a pricey option. They'll use liquid cooling. So essentially you have pipes running through your server full of cold water, and that cools down the air surrounding it. So instead of blowing air, it just cools down the air by taking in that thermal energy. This works in very much the same way. Okay, so there's your condenser, pumps the water right back into the boiler, and the whole process starts again. Okay, now, the turbine, when it's rotating, this electricity goes through a generator, and that is how the electrical power is produced. Those electrical powers then go through your power lines, right? The major power lines, which then get diverted to the simpler power lines on your street that eventually connect to your house. Okay, so the first thing we're going to look at are fossil fuel power stations. So the first thing is going to be coal burning. All right, so we're adding coal into the bottom of this boiler. Okay, so when you burn the coal, there's a lot of heat generated, and inside, like I said, inside this boiler, the water starts to heat up and boil, as you would imagine. So steam is produced, that steam gets pushed through these pipes, right? So the steam goes and turns a generator, well, it turns the turbine, which then turns the generator, which produces your electricity. The steam then comes down these pipes through the condenser, right? There's cold water moving through the bottom, moves through this, becomes liquid water, and gets pumped back into the boiler. So this cycle repeats itself. Now, if we want to look at this from the perspective of a Sankey diagram, you've got the chemical energy from the coal. Okay, so that chemical energy is then getting converted into hot steam of the water, which then is getting pushed through the pipes and then turns the generator. And of course, in the meantime, there's some exhaust gas that gets left pushed out of the top. So that's loss of energy, inefficiency. Now that steam turns the turbine, that's kinetic energy as it's rotating. But of course, there's going to be some energy loss there as well. Okay, so there is some heat that gets wasted. There's also a little bit of friction there, so that can also be indicated. So that steam then comes down, like I said, this cold water gets pumped through a pipe, that steam condenses back to liquid water, goes back into the boiler. So finally, your end result of all of this is electricity, which, and you know, with electricity, there's resistance as well. This friction, this is the friction from the rotating turbine. Now, if you wanted to add another piece of heat or energy loss here, that would be the resistance as the electrons move through the electrical wire. Now, on the bottom right of the slide, you see power plant efficiencies. Now, this is definitely not all the types of power plants, but this is for coal and oil burning. Notice that oil, pulverized coal, and coal, they're all at about 40% efficient. You don't really need to worry about what pulverized coal is. Essentially, pulverized coal, it's regular coal that is treated so that it all burns, so it's a bit more efficient. And I know that's not exactly represented here in the diagram, but in reality, pulverized coal is intended to be more efficient, but that's for a larger scale operation. Okay, so now we're going on to gas burning. Okay, so gas burning, this would be your natural gas. So natural gas, that's what you have in your house. Okay, so your furnace, this is how your hot water tank, most likely that's how it boils unless you have a different system. And so this is another method. You've got gas. In the region where normally you would put coal, now you have gas, and that gas is burning. Now there is so much force from the heat of this gas burning that you can actually have a second turbine here. This is called a gas turbine, and it is within the well where the gas is burning. Okay, so this upward force will rotate the gas turbine, and that rotation allows electricity to be generated. So you, I guess, bypass all of this water and steam and, well, the turbine turning. It goes directly into a turbine rotating. So you have electricity generation right from the get-go. Now, of course, this is still heat, so we can get electricity using the other method as well. You've got the water in the boiler, and the water boils, becomes steam, goes through these pipes, rotates the turbine that produces electricity, and the rest of the steam comes down, condenses in the region with cold water, and comes back to the boiler. Okay, but both of these processes produce electricity, and this is why burning gas is more efficient than burning coal. Okay, so method number one, you go directly from the chemical energy of the gas directly into electricity, right? So that's this bottom process here. And of course, there's some friction as the turbine rotates. Anytime you have things rotating, there is friction, solid friction. Okay, so the other method is just like what we had before. The chemical energy becomes hot steam, right? And of course, there's some kind of exhaust at the top. Okay? And that steam translates into the kinetic energy of the rotating turbine. And just like before, you have some loss of heat there as well. Okay, and finally, that kinetic energy gets converted to electricity. And there is some friction there again because you have a rotating turbine. Excuse me. So what we notice is that we have electricity generated in two different ways. And this is why, looking again back at the bar graph, we can see that natural gas has around 50% efficiency as opposed to the 40% from the coal. Okay. All right. Now, the majority of today's video is focusing on nuclear power stations. Now, whether it's coal, oil, or nuclear, they all produce electricity in pretty much the same way. You have something that heats up water, okay, and the water becomes steam, the steam turns a turbine, the steam then cools, becomes liquid water, and the whole process starts over again. The difference between all three of these types of energy production is how does the heat get created? Okay, so with the coal, you burn the coal, it produces heat, and the water boils. With the oil, you burn the oil, and either that rotates its own turbine or it boils the water again. With nuclear, what we're really focusing on here is how we generate heat. Okay, so a lot of the next series of slides is going to be understanding how the nuclear reactor works, how we get the uranium, how we enrich it, and how overall it works in the reactor to produce the heat. But let's start off with this big picture idea again. Remember, all of these reactors work more or less the same. It's just how they produce the heat and how they heat the water that's really different. Okay, so looking at the big picture, that's really a generalization that we can make. So this piece right here, the piece that is glowing red, orange, and yellow, okay, this is where the heat is generated. You're going to notice something called a reactor vessel, control rods, and pressurizer. Pressurizer, that's just like before, it releases extra pressure from the system, but you have this flow of heat. Over the next several slides, we will talk about how this heat is created, what the control rods are, where the reactor vessel is, and how it works. All of these will be explored. But for now, just understand that there is heat flowing through this system. Now, part of that heat is going to be passed down a pipe that is inside a deep pool of water. Okay, so that creates this water, makes the water heat up. Those of you who have ever really looked at your hot water tanks at home, it's that big cylinder next to your furnace. A lot of the old hot water heaters, they have a heating element in the bottom corner, and that heats up the rest of the water. It's not the most efficient process. Okay, so newer hot water boilers, they've got a metal pipe going down the center like this. Okay, so it's a concentric cylinder with the actual vessel, okay, with the actual tank of water. And it uniformly heats up the water, thereby using less energy. So this is quite an efficient process. All right, so this heat inside of the pipe heats up the water around it. The water boils, becomes steam. The steam gets pushed through these pipes, rotates the turbine, which rotates the generator, which thereby produces electricity. Okay, the steam moves past the turbine afterward, gets cooled down. So this is cold water moving through these pipes, becomes liquid water, and that liquid water gets pushed back up into the tank, and the process repeats itself. So, exact same thing that we've seen before, except, well, how are we producing this heat? Okay, so when we look at the energy transformations, well, the first one's a little bit different. Okay, instead of using chemical energy, we're using nuclear energy, and that's becoming heat. And in a sense, nuclear energy is like chemical energy. Everything is chemical at the end of the day. Okay, that's becoming heat. It's becoming kinetic energy in the turbine. And that becomes the electrical energy which you and I use. Moving on. Now, let's look at the Sankey diagram for a typical nuclear reactor. Now, it says here, because of the difficulty of enrichment, include that energy in the diagram. Now, you don't know what enrichment is yet, but it is a process used to obtain a certain density of the required uranium for nuclear fission. We are going to be talking quite a bit about enrichment over the next couple of slides. All you need to know is that it's a very expensive and slow process, and it is a very, it's very time consuming, okay? But it uses a lot of energy. So it should be part of this Sankey diagram. So the first thing we start off with is energy in the uranium ore, okay? Ore means it's coming from the Earth's crust. So you go to the Earth's crust, you find a region where there is a high amount of uranium, and you extract it from the Earth. Now, we do not just take the uranium from the Earth's crust and throw it in a nuclear reactor. That uranium needs to get treated. And that uranium gets treated, and it gets what's called enriched. Okay? Enriched uranium just means it's higher density. And if you're wondering, the uranium we're talking about here is uranium-235. This will come up on the slides later on. Now, when you convert or when you process this uranium ore and make it enriched, you use energy. So some of that energy is lost, and we cannot use it in the overall reactor. Okay, after you enrich the uranium, you get to produce electrical energy. And of course, you have energy lost there as well. On the previous slide, when I was explaining the process where we're creating nuclear energy, there's actually a lot of things missing right here in the middle between the orange and the purple arrows. Okay, so you take the uranium, well, there's a lot of things that happen here. You've got that chemical/nuclear energy. You've got the hot steam. You've got the kinetic energy, and we'll be looking at that on the next slide. And there's your heat loss. Okay. What transformations were not shown in the previous Sankey diagram? Okay, so like I was just saying, we didn't show, overall, we did show that there's electrical, but we didn't show the hot steam, and we didn't show the kinetic energy. And with those additional two energy transformations, there are additional sources of heat loss. Okay, so heat loss and friction. Okay, now these next two slides are going to be very dense with knowledge. There is going to be a bit of chemistry here as well. You don't need to focus on the chemistry as much. It's more for your information. What you just need to understand are the facts presented here. And understand that there are two ways in which we enrich the uranium that's coming from the Earth's crust. Okay, so first things first. To work properly, a reactor needs a higher proportion of uranium-235 isotope that occurs naturally. Okay, so when you have the uranium ore that you extract from the Earth's crust, it's made up of two things. It's made up of uranium-238 and uranium-235. These are two isotopes of uranium. Now, only uranium-235 is capable of the fission reaction. If you take uranium-238 and you bombard it with a neutron, which is essentially how the uranium-235 breaks down, if you bombard the uranium-238 with a neutron, it'll just become uranium-239 and it'll just sit there. It'll become a different isotope. Now, when you extract the ore from the Earth's crust, the natural uranium is about 0.72% uranium-235 by mass. Okay, so we do something called enrichment so that it becomes about 2 to 5% uranium-235 by mass. And in order, the reason we do that is so that we have enough mass of uranium-235 to sustain a fission reaction. Right? Now, next point. One slow and expensive means of enrichment for uranium is called gaseous diffusion. So there's two methods that we're going to look at. The first one is this one, gaseous diffusion. So uranium, now keep in mind this is the uranium with the uranium-235 and 238. You purify it and you combine it with fluorine. Okay, so fluorine is one of those elements on your periodic table, and when you combine it with fluorine, you get a gas called uranium hexafluoride, UF6. Now, the fact that you had uranium-235 and 238 in the uranium means that you're going to have two almost versions of uranium hexafluoride. Okay, and each of those versions has a different mass. Okay, so look here on this diagram. This is a simplified version of what's actually happening, but nonetheless, it gets the point across. So notice in this tank, we have a very small volume. So this gas is under very high pressure, which allows it to get forced into this larger container. Okay, here's UF6, your uranium hexafluoride. Notice that there are red dots and there are green dots. Okay, the red dots are uranium hexafluoride with the uranium-238 isotope, and the green dots are uranium-235, the uranium hexafluoride. The reason the green dots are smaller is because it's less massive. Now, the difference in size here is obviously exaggerated. It's just done like that so you can understand visually what's going on. Okay, so remember that these numbers here, the 235 and the 238, these are mass numbers. That's telling you how many neutrons and protons you have in the nucleus. So in reality, the uranium-235 UF6, it's only, 3 atomic mass units more massive than this one here. But nonetheless, the idea is it's more massive, it's a little bit bigger. Okay, so what happens is when you have all of these atoms, you push them through a membrane. And the membrane is done in such a way that the ones that are smaller, the atoms that are smaller will be able to easily pass through, and the more massive atoms will have a more difficult time passing through. Okay, so what you notice is now on top, you have a greater percentage of uranium-35 isotopes compared to uranium-238. And so the amount of gas that gets pushed through this next pipe, this is a higher percentage of uranium-235. And that's now what we call enriched. It's a higher density of this particular isotope. And of course, the one with the less uranium-235, that's pumped through the bottom. In reality, the gas gets pumped through many different membrane filters, but again, this picture is just meant for you to understand generally what's going on. Okay. Now, to work properly, a reactor needs a higher proportion of the uranium-235 isotope of uranium than occurs naturally. So we saw this on a previous slide. The second means of enrichment, and also this is slow and expensive, it's called centrifuging. So any of you who have ever maybe volunteered in a hospital or seen how this works in a hospital, you would have seen that a centrifuge is a device where they place vials of blood and this machine rotates it at a very high speed. So it separates different particles of the blood, different proteins. Centrifuging has a lot of important applications in science. Another application of it, significant here, is, well, separating the uranium-235 with the uranium-238. So after you react the uranium with fluorine and you get uranium hexafluoride, you place it in the centrifuge. Now notice at the bottom here you've got that arrow. This is indicating that this machine is rotating, and it's rotating at very high speed. And what it essentially does is it forces the heavier uranium-238 to the outside walls, while the less dense, lighter uranium-235 stays toward the axis of rotation. It doesn't move that far. And so the less dense uranium-235 stays here, so that comes out, and you have your enriched uranium-235, and the more dense moves through these outside pipes. That's the uranium-238. Now, if you're wondering why can we not just put the uranium here and do that process, why do we have to react it with fluorine? Okay, well, when you force the uranium to react with the fluorine, there's a slight separation of molecules of the uranium-235 and 238, something that you wouldn't have originally. Not to mention, now you have it in a gaseous state, not a solid state. Okay, you can't use a centrifuge in a solid state. It's got to be a fluid. Okay. Now, the bottom box here on the slide just further brings up the point again that there is a lot of energy in this process. And that's why a couple slides ago when we made the Sankey diagram, it said, due to the process of enrichment, well, we have to include that in the Sankey diagram because it's slow, it's expensive, and it loses a lot of energy. Okay, so this slide is showing us a general visual representation of what's going on. So first thing that is done, the uranium ore gets mined, okay, from the earth. Okay, then that uranium ore gets refined, it gets purified, and then it undergoes some kind of conversion. So you start off with this ore that is made up of both uranium-235 and 238, and it undergoes a process called yellow caking. Okay, this yellow caking is, well, reacting the uranium ore after it's been purified with the fluorine. And if you actually Google image yellow cake, this is what the uranium looks like after it's been reacted. It actually does look like yellow cake. All right, so you have your UF6. This undergoes either gaseous diffusion or centrifuging, okay, and it undergoes enrichment. So some of that extra uranium hexafluoride gets stored if we're not using it. Of course, that gets stored in a container. Enriched uranium hexafluoride we can then use in the nuclear reactors. Okay, so fuel fabrication, well, we have to create these uranium pieces into rods. You'll understand the role of rods as we explore this more in the slides. All right, this is a really nice graph. Nuclear share of total electricity generation. Now, notice that these percentages, this is showing you how much of each country's total energy usage is coming from nuclear reactors. Now, this is data from 2007, but the numbers really haven't changed all that much. What I want you to notice is France. Okay, so France is, well, most of its energy is coming from nuclear energy, 77%, and it is the highest on this list. Okay, so France is actually the world's largest net exporter of electricity due to its very low cost of generation. Now, what's really interesting here is France creates more electricity from nuclear means than it actually needs. So it ends up selling this electricity to other countries. And believe it or not, it brings in about 3 billion euros per year just from this. Okay, so to read more and learn more about this, check worldnuclear.org. Okay, so fission. Those of you that studied astrophysics for the IB, and even if you didn't, rather, we've all learned a little bit about nuclear fusion. Fusion is when small light atoms combine into a heavier atom, so they combine. Fission is when you have one large atom and it splits spontaneously into two lighter atoms. Okay, and those lighter atoms are called the daughter nuclei. So we did this in grade 11 physics. You've got the parent atom and you've got the daughter nucleus. Usually you have more than one. Okay, so here's one example of a fission reaction. Now, although it's not just uranium-235 that gets used in nuclear reactors, we'll see in a couple of slides that there's actually different kinds of radioactive elements you can use. This is a very popular one. Okay, so this is the one we're going to focus all our energies on right now. Uranium-235, so that 92, that's the atomic number of protons. When you bombard it with a neutron, so there's the neutron, it becomes uranium-236. Now, if you remember from grade 11, when there's a star here, what that means is it's in a very high energy state, and it is unstable. And that unstable uranium-236 is going to break down into xenon-140 and strontium-94 plus 2 neutrons. Now, when uranium-235 breaks down, it doesn't have to necessarily break down into xenon and strontium. It might break down into other fission products. Sometimes it breaks down into krypton and barium, and it releases 3 neutrons. It might even break down into cesium and iodine. There's a few different combinations. Not every combination can occur, but there's a few that can spontaneously occur. Okay, so let's take a look at this. You have your uranium-235 atom. It gets bombarded with the neutron, and it becomes this unstable uranium-236, which then breaks down into xenon and strontium, releasing 2 neutrons in the process. Now, those 2 neutrons, notice your uranium-235 atom, the whole series of this spontaneous reaction started with it being bombarded by 1 neutron. After this reaction is done, there are 2 neutrons left over. Each of those neutrons can then bombard another uranium-235 atom, causing it to then, each of them, make another 2 sets of byproducts and 2 more neutrons each. So what you should understand from this is that what you really have here is a chain reaction. If one uranium-235 atom gets bombarded with 1 neutron and its end reaction produces 2 neutrons, that can then cause another 2 uranium-235 atoms to decay, okay, which then will result in 2 of each of those, which is 4, and then 2 of each of those, which is 8. Okay, so you end up with this chain reaction. Okay, so you have your primary, your secondary, and your tertiary steps, and actually this can keep going on forever. Now, a couple slides ago, I said that we need to enrich the uranium so that we have a higher proportion of uranium-235 than what you start with. So what I said was, originally, when the uranium gets extracted from the ore, it's about 0.72% uranium-235. And in order for this to work properly in the nuclear reactor, it has to be between 2 and 5% uranium-235 by density. Now, we not only need a certain density of the uranium isotope, we need a certain mass of uranium-235 of this uranium rod to initiate the nuclear reaction. And that minimum mass is called the critical mass. If you notice on this table, we've got different nuclides here. All of these nuclides are used in nuclear reactors. So you have uranium-235 here near the top. You can also have uranium-233, neptunium-236, all the way down to plutonium-242, and all their various critical masses here. So it looks like we need 52 kilograms of uranium-235 to initiate the nuclear reaction. Notice there's something here, that first column, or rather the second column there, half-life. So from grade 11, we learned half-life is the amount of time required for half of the radioactive substance to decay into a stable form. Uranium-235, that's very, very long, 704 million years in order for half of it to decay to a stable form. And this is one of the big problems of nuclear reactors. You have these radioactive byproducts that end up being produced with a very large half-life. And they need to be stored in containers until the radiation leakage is minimal. And well, we can then use it for other means. Something else to notice in this list is that there is no uranium-238. And this is something that I mentioned earlier. And this is why we have to get a higher density of uranium-235 than what we start with. Uranium-238 will not undergo a fission reaction. If you bombard a uranium-238 atom with a neutron, it will just become uranium-239 and it will stay like that. Okay, this is why we enrich uranium. Excuse me. Now, what you saw just a couple slides ago is that with your reaction, so when you have uranium-235 and you bombard it with a neutron, you end up with some byproducts, which are radioactive, by the way, and you get 2 neutrons. Now, I did mention that you don't necessarily have to get xenon and strontium and 2 neutrons. You could also get krypton and barium with 3 neutrons. But overall, usually you get about 2 or 3 neutrons being given off. And those will then set off their own nuclear reactions, which will then set off their own nuclear reactions in a chain reaction. What you have to make sure when you have a nuclear reactor is that the series of chain reactions are controlled. You do not want this to be a runaway effect that you are not in control of. When you're dealing with something like a nuclear bomb, this is where having an uncontrolled nuclear reaction is preferred, because you want this reaction to be very fast, very strong, and there is really no need to control it in that sense. Now, with the controlled scenario, like it says on the slides, half of the product neutrons are absorbed by the control rods, and in the second case, where it's uncontrolled, very few of the neutrons are absorbed. If you absorb the neutrons, well, then you don't have that neutron to react with another uranium-235 atom, thus creating a new nuclear reaction. Now notice it says control rods. We haven't yet talked about what control rods are, but I think you're getting the idea now. The control rods are some kind of rod within the nuclear reactor that absorb neutrons, and it helps us to control the reaction. Okay, so recall that a typical fission of uranium-235 will produce 2 and sometimes 3 product neutrons. Now, those neutrons, depending on how they're made, they can have any kind of kinetic energy, any kind of speed. The mass of the neutron, that's the same, but the speed is going to change. If your neutron, so here in this slide I have the uranium-235 atom, here's a neutron. If the neutron is moving too fast, it will just pass right through the atom. If the neutron is moving too slow, it will just bounce off. Also, it will not, well, it won't excite it, it won't cause a reaction. You need that neutron to be moving at exactly the right speed. Okay, in order for it to run at exactly the right speed, what ends up happening is these neutrons end up moving in something called heavy water. Heavy water is water that is about 10% denser. And that's enough to slow down the neutrons so that it properly interacts with uranium-235. So most of the neutrons are fast. So you can see most of them have an energy based on this graph, well, between 1 and 2 mega electron volts, most of them. So on the y-axis here of this graph, this would be the number of neutrons. Here you have most of them lie within this energy range, 1 to 2. So a couple things can happen. Okay, so these fast neutrons will either be captured by uranium-238. So remember, these fuel rods of uranium, it's even though we enriched it so that it has more uranium-235 than what it started with, it still has uranium-238. We never removed that. Okay, so you still have uranium-238, so the neutrons can just be captured by the uranium-238, becoming uranium-239, or they can just leave the surface of the fuel rods. And so moderators are placed in between these fuel rods. These moderators will be things like I said, heavy water. You can also put graphite. You can put light water, and it all depends on the scenario. And this will slow down the neutrons to the right speed so that they continue the fission process. Okay, now we've got more rods getting inserted. So far we've got the uranium rods, we've got the moderator, and now you've got something called control rods. So this diagram in the middle, this shows us the 3D representation of what's going on. Notice that these control rods can either be pushed into the reactor or brought out. Okay, so the control rods are what are being used to adjust the rate of reaction. Remember that this is not a nuclear bomb. You do not want a runaway uncontrolled effect. You want to be able to control the rate of nuclear reaction. If you take out the control rods, the reaction rate will increase. Okay, so why would that happen? Well, the control rods are usually made up of something like boron. Okay, boron is a neutron-absorbing element. This will reduce the number of free neutrons and take them out of the reaction. So if you put them in, that's going to decrease the rate of reaction, and if you take them out, it will increase the rate of reaction. Okay, cadmium is also another element that can be used for these control rods. Now, sometimes instead of heavy water, there might be another type of fluid that is used. Okay, so we're going to look at that on the next slide. Okay, so sometimes another thermal absorber can be circulated. Well, let's talk about that. Remember, what we're really doing right now is understanding how the nuclear reactor produces heat. We looked at how the coal power plant works. We looked at how the oil power plant works. And we said that the nuclear power plant is exactly the same. You want water to boil. The steam then moves through a system of tubes. It rotates a turbine. It generates electricity. The steam cools down into water and goes back inside of the boiler. That process is the same for all three. For coal, we said that we burn the coal. For oil, we burn the gas. Now, this whole series of slides is explaining to us how are we producing heat from the nuclear reactor. And this is how heat is produced through these reactions. Okay, so when you have uranium undergoing fission, there's a lot of heat released. In addition to the neutrons that get released, in addition to the byproducts, whether it's krypton, strontium, barium, whatever it is, you have a lot of heat released as well. And that is the heat that heats up the water and boils it, produces steam. Okay, so remember, the whole purpose of the reactor core is to produce heat through fission. Okay, so we have fuel rods, we've got the moderator, we've got control rods. They're all surrounded by water. Sometimes they can be also surrounded by liquid sodium. Now, just ask yourself for a moment, why might they use liquid sodium instead of water? So pause the video if you'd like at this point to think about it. Liquid sodium would be preferable compared to water because sodium will not corrode the steel reactor parts. As much as they can be careful to use distilled water, there's always a chance that you have some kind of impurity and eventually will cause corrosion and rust. Okay, so then that extremely hot water from the reactor core, right, because the water is getting heated up, the hot water from the reactor core gets sent to the heat exchanger, which then acts like a boiler, like it does in the fossil fuel power plant. So we'll see that on this slide. Okay, so here we see this system again. So the heat exchanger, so here are our control rods, here's the heat exchanger. Okay, so the heat exchanger takes heat from this reactor, right? That's what makes the water heat up and become steam. We've got the turbine rotating, right? The steam comes back down to the condenser and then becomes liquid water, which moves through this whole cycle again. The generator at the same time producing electricity. Excuse me. Now, when you have a nuclear reactor, there is always potential for risk. And this is one of the major reasons why, well, not the only major reason, but one of the major reasons why some people are against using nuclear reactors because of the possible damage that they can cause. Okay, now, the damage they can cause is like a natural disaster. While it's rare, it can happen. Now, the other downside of the nuclear reactors is all the nuclear waste that's produced. And you can see some of the half-lives range from thousands to millions and hundreds of millions of years. So in order for you to wait for those radioactive pieces to settle down, to become stable, it takes a very, very long time. Okay. So in order to protect the reactor itself from radiation leakage, there are three main zones that get protected. Okay, the first zone is called the reactor coolant. Okay, so that's over here. This is getting controlled. This is getting an extra barrier around it. Zone 2, the heat exchanger. This is also an isolated and protected zone. In zone 3, the cooling tower. This is also protected from radioactivity. Now, usually a concrete liner houses the reactor's pressure vessel. So that's right here. Usually this is a concrete liner, and it also acts as a radiation shield. Okay, so that liner in turn is then housed within a much larger steel containment vessel. The steel serves as a barrier to prevent leakage. So you have two layers. You've got the concrete layer and then you've got the steel. Now, I'm sure many of you have heard and they are familiar with the nuclear incident that happened in Chernobyl during the Soviet Union. Okay, they did not have a secondary containment structure, and that is what allowed the radioactive material to escape. The first layer of concrete was blown, and they did not have a second layer to contain the radiation, which then spread across the globe. Okay, we are not going to be moving on to this slide until the next video, so at this point you can stop. Stay tuned for the next video, 8.1, video 3 of 4. The next video is going to be focusing on these practice problems. So whereas this video was mainly conceptual, understanding how the nuclear power plant works, how it generates electricity, the next one will be much heavier in practice questions, and we'll also look at wind energy and the calculations associated with that. So stay tuned next time.